Okay, it's 11. Obina, it's your show.
Okay. So, yeah, good morning all, and welcome everyone to the second day of the Quantum Thermodynamics Conference. And our first speaker today is Sebastian Deffner from University of Maryland. So, Sebastian, you now have the floor.
Great, thank you. Thank you very much for the opportunity to talk and tell you a little bit more about the work that we're doing. So last night, many of you might have already seen the talk by my student Nathan, and he focused very much on what we're doing with quantum engines. Now, what I want to do is I want to talk about a problem that you might not necessarily immediately relate with quantum thermodynamics, but which has a very, very clear thermodynamic motivation and which might be a starting point for interesting and important questions that we actually should address in thermodynamics. So in particular, I will be talking about these speed limits, which many of you might be familiar with, and I will be putting that in relation and contact with information production rates or entropy production rates. So as Obina said, I'm at UMBC, and this is where the money comes from. Now, this is the last week of November, which means in America, we're in the season of grad school applications. Therefore, I'm contractually obligated to show you this slide to give you a quick idea of where I could be if I was at home. Well, actually, right now I'm located in Kampala, Uganda. But if ever this global insanity will come to an end, I will return to Maryland. And this is an area view of campus. This is our university. The physics building is very, very easy to recognize. It's the one with the observatory. And usually if everything goes as planned, this is my office right here, this window. We are the second largest university in the university system of Maryland. We have about 50,000 students, of which 3,000 are graduate students, plus master and PhD students. If you're interested in what we're doing in physics, we have 4 core areas: quantum optics, quantum information, condensed matter, atmospheric, and astrophysics. And what you notice, obviously, there's no section or sub-department or whatever in quantum thermodynamics. In the US, quantum thermodynamics is still horribly underrepresented, and they have no idea where to put people like us. This is why I'm officially listed under quantum optics and quantum information. I'm co-listed under condensed matter physics, and now they've even added me to astrophysics. So thermodynamics is everywhere. Now, what is it that I actually want to talk about? And since this is the first talk of the day, I thought I'd ease you a little bit into what we're interested in. So what we're looking at are quantum technologies. So what we would like to better understand is how the thermodynamics of these quantum systems can be described and what the thermodynamic questions are that we need to address. Now, these are just a few pretty pictures, like Google's Sycamore, which chip is somewhere in here, Microsoft's integrative, well, doesn't really matter, so the chip is somewhere in here, and you have these smaller startups. Now, what we would like to understand about these systems is not only what Feynman said, namely that these are great systems to understand nature, in the sense that if we want to understand the quantum reality of nature, we actually have to make a quantum mechanical simulation. But also that quantum mechanics is weird in the sense that, and this is what Roger Zurich said, the only failure of quantum theory is its inability to provide a natural framework for our prejudices about the workings of the universe. This means nothing else than when thinking about the thermodynamics of these quantum systems, we are often driven by classical intuition, which is not necessarily the best way to think about quantum systems. There are quantum peculiarities, there are additional resources. And we've seen some of this yesterday already in Janet's and in Felix's talk when they were talking about exploiting, utilizing quantum coherence as an additional resource. Now, when thinking about quantum computation in particular, or more generally about quantum technologies, Deutsch's statement is actually spot on, who said that quantum computation is nothing less than a distinctly new way of harnessing nature, which means what we're doing in quantum thermodynamics, at least to my mind, is trying to understand the thermodynamic resources or the thermodynamic costs that are associated with using something that is generally quantum, such as quantum correlations, quantum coherence, quantum entanglement. Now, what I want to be focusing on today is entropy production, which is an inherently thermodynamic problem. And in particular, I want to look into entropy production rates. These are questions that are surprisingly old, so they actually go back onto the 60s, where Bremermann and then in the 80s Bekenstein already derived a couple of interesting bounds that may be of quantum thermodynamic relevance. Then I will continue to talk about Pengery's bound, which is actually exactly as old as I am. And then I will talk about how this is put in context of quantum thermodynamics. In the second part of the talk, I will focus on a little paper that I wrote earlier this year, in which I picked up some of these old ideas and put them more in a modern language and try to understand how, from a more consistent modern quantum thermodynamic framework, we can think about how to bound information and entropy production rates by means of these quantum speed limits and by using only results from information theory. Now, fair disclaimer, some, maybe even many of you might have seen a version of this talk before. And I'm talking about exactly this topic again, not only because I was lazy and I didn't want to prepare a second talk, but also because I think this is an essentially important, crucially important problem in thermodynamics that deserves more attention and that as a community we need to think more about. All right. So to start, the problem goes back to the 60s when Bremermann asked the following question, or he actually started with an observation. Whenever you have a computational device, and back then they were thinking about the big IBM machines, but also if you have something like your cell phone that does something, that does a computation, then this computational device has to obey the fundamental laws of physics. In particular, these fundamental laws are special relativity, quantum mechanics, and thermodynamics. Here you go. We already have quantum mechanics and thermodynamics in the thinking of how to think about computational logical devices in the 60s. Now, special relativity is probably not something that we think about most frequently because typically we're not quite worrying about relativistic corrections of thermodynamics yet. However, stay tuned. Together with Obina and Nathan, we're currently also looking into the thermodynamics consequences of special relativistic effects and the light column. But for the purposes of this talk, I only want to focus on quantum and thermodynamics. The conceptual questions that you immediately need to ask when thinking about these quantum technologies then is, well, quantum mechanics is weird in the sense that we not only have these additional resources, but we also have genuine quantum effects, genuine quantum peculiarities. In particular, and this is the hallmark result, there's Heisenberg uncertainty, or to be more precise, indeterminacy. In other words, if we have canonical sets of variables which not commute with each other, then we get the famous uncertainty relations. Now, the uncertainty relation that is somewhat different than many of these other things is the uncertainty relation for energy and time. And the problem basically boils down to the time is not typically represented as an emission operator, which means the usual computational relations cannot be at the core of this uncertainty relation. However, we do know that the uncertainty relation for energy and time exists. And the immediate question, and this is the question that Bremermann asked us, how does this quantum uncertainty relate to processed information? What does it tell us about how information can be processed in quantum systems? Bremermann's suggestion was actually somewhat naive. So basically what he did was he took a textbook on quantum mechanics, took a textbook on information theory, and started comparing symbols. For those of you who are familiar with information theory textbooks, you will know a lot about Shannon's noise energy, which is basically just computing the error rate of information communication through classical channels. In some way in there, there's a delta E, which quantifies the energy fluctuations in the classical channel. So what Bremermann did was he said, well, there's a delta E, some uncertainty quantifying the error rate. There's another delta E, which comes from quantum mechanics. So they have to be the same. And he simply equated them. And if you do that, well, then using the uncertainty principle for energy and time, you do get something like an upper bound on the rate of entropy production, which comes directly from this quantum uncertainty. Now, the problem with that is, well, that can be right. I mean, you cannot just simply take two textbooks and compare symbols without any physical foundation. And this was clear very, very early on. And after Bremermann's paper, there was a flood of other papers directly attacking his argumentation. And the question was whether such a bound can even exist. It took about 20 years, 15 years, before Bekenstein revisited the problem, but this time in a physical, more rigorous way. So Bekenstein, so some of you might be familiar with him because he developed this black hole thermodynamics, which means he came from cosmology, and what he was very interested in was trying to understand regions of space that are weird in a different sense, but that we cannot access directly, in particular with thinking about singularities in space-time, black holes. So he started with the following consideration. Now, if we can't access a given region of space, which means if we can't take a measurement, can we at the very least bound how much entropy or information can be stored in this given region of space? And this is what led to the Bekenstein-Hawking entropy, which we have here, which is the maximum amount of entropy that can be stored in any given region of space, which only depends on natural constants, Boltzmann's constant, h bar, and the speed of light. It depends on the surface area, 2 pi r, where r is the the Schwarzschild radius, and E is the energy of this black hole. Then what you can do is you can ask the following question. If this is the maximum amount of entropy that is stored in a given region of space, which I can relate to information, which simply changing the units, how long does it take for all of this information to evaporate, to come out of the black hole, which has to be given, well, it has to be lower bounded by the time it takes to traverse the event horizon at the speed of light. So this is the minimal time necessary for information to come from the center of the black hole to the event horizon. And then simply dividing this total amount of information that is stored in a black hole by the minimal time it takes to come out, you can derive something like a maximal rate of communication. So this is the maximal rate with which information can come out of black holes. If you do all of that, simplify a little bit, what you end up with is actually an incredibly appealing bound, because then all of a sudden this maximal rate of information, which is defined as maximal amount of information divided by minimal time, it's just given by pi, natural constant, whatever, h bar, the energy of the black hole, and log 2. I also can rewrite that. I can rewrite that as the ratio of energy divided by information, which then quantifies how much energy is necessary in order to communicate a single bit of information. And if you look at that, this bound looks incredibly appealing because it should strongly remind you of Landauer's principle, right? So you have an energy here, you have log 2, you have information. So this looks very much like a quantum version of Landauer's principle for communication. No, there's an h bar. So that's definitely quantum. And everything that we need here is a derivation that only depends on the black hole entropy and special relativity. By the way, I just realized that Zoom apparently turned on some grid over my slides. I'm not entirely sure if you're seeing that or if it's just on my side.
Yes, it's there.
Okay, so let me see if I can remove that grid. Sorry for that. Is it just me, or does Zoom constantly update something?
Probably they want just to make it easy for people to follow the line if you are writing long tests.
Does anyone know how to turn that off? Sorry about that. 1 second and then we continue. So just the other day I gave a talk.
But it's not bad. So, and then I think Felix is also mentioning that it is not distracting. So.
If it's not distracting, that's fine. So let's try this. Is this better?
Yeah, it's much better. Thank you.
It's on now.
I apologize. So last time I used Zoom, which means yesterday, I didn't have these lines and all of a sudden they're here. Okay. Okay, where was I? Okay. So now we have this upper bound on the rate of communication, which only depends on the black hole entropy and special relativity. All right. Now, let's think a little bit about what we have achieved and what we want. So we have achieved a nice thermodynamic, maybe quantum thermodynamic, well, there's an H bar somewhere in there, bound on the rate of communication, which depends only on fundamental observations, fundamental physics, namely the black holes. And we know that there are even specific systems, namely black holes, that saturate these bonds. So to a certain degree, we've used some version of quantum speed limits, well, not quite, it's a bound from general relativity, and we've been talking about quantum communication. It's the total amount of quantum information stored in black holes. But in all honesty, this cannot be satisfactory because what we've used here are just plausibility arguments, where we're using the entirety of the entropy stored in a black hole, and we divide that by some minimal time that is given by the time it takes to traverse the Schwarzschild radius, the event horizon. Well, that can be solved. Or in particular, that can be tight. So this has to be a very, very loose bound. From a more fundamental physical point of view, we actually assume that we can extract the entirety of the information that is stored in a given system. So how exactly are we going to do that with black holes? But remember how I started out with. So the question that we want to ask is, we want to apply that to quantum technologies, in particular quantum computers. So do we really need to determine the energy of a black hole in order to bound the rate of communication in quantum technologies? Probably not. So we need to do better somehow. And this is also a very old question that was addressed already in '83 by Pendry, who said the following. Well, rather than having to rely on black holes, let's see whether we can actually say something directly about communication, where communication in his sense should be carried by photons that come through a classical channel. Then if we want to detect n bits of information, since these n bits of information are carried by quantum particles, quantum information carriers, each of these quantum carriers has an uncertainty of delta E, which is just given by the uncertainty principle. So delta E is then roughly determined by h bar over t, where t is the time it takes for the quantum particle to be detected. Now, further assuming that each of these information carriers carries the energy in h bar over 2t, and combining these two bonds, you find that the energy current is lower bounded by energy current, E dot, that's the heat transferred, is lower bounded by 1/2 h bar n squared over t squared. Okay, now this is maybe again very hand waving and not entirely clear where all of these bounds come from. But what he did then is in this paper, he go through a rather lengthy 15 pages derivation, looking into the distribution of information carriers, which are photons, therefore looking at the Bose-Einstein distribution, identifying the rate of communication of information transfer as number of bits divided by time. And what he ends up with is that the rate of communication squared is given by this thing here. Now, this derivation is nice in the sense that it relies only on statistical mechanics. So we don't need any black hole thermodynamics or anything like that. And it only depends on the uncertainty relation for energy and time, which means quantum speed limits are more directly tied into that. What is not that appealing about this bound is that we now have an upper bound on the rate squared, which means an interpretation as some form of dynamical Landau's principle is not as immediate. However, I like talking about this paper because this gives a very, very good motivation for revisiting the problem. Because what we should be able to use notions of statistical mechanics, or maybe information theory in a broader context, and this uncertainty relation, Heisenberg's uncertainty relation for energy and time, to derive bounds on the rate of communication that are directly applicable, which are directly applicable for the kind of questions we ask. This is something that we started looking into about 10 years ago, which is a paper that you might have seen, or so many of these results are very, very well known in this community. In particular, you know that the entropy production in isolated quantum systems is just given by the relative entropy between the time-evolved density operator and the corresponding equilibrium state, the Gibbs state. What we did back then was we used the quantum speed limit, which I will make more precise in a slide, which back then was simply given by Margulis and Leventin, Mandelstam, and Tom, or actually a little bit more generalized, where the quantum speed limit time is given by the maximum of either the energy or the energy variance, and L is just the angle between initial and final state. What we then did was we basically followed Bekenstein's original argument. So we simply took the total amount of entropy production divided by the minimal time, the quantum speed limit time. And after a little bit of hand-waving magic, you do end up with something that looks very much like Bekenstein's bond, or this dynamical Landau's principle for communication, which is that the maximal entropy production rate is just given by twice the energy and some stuff which only depends on the specifics of the system. Angle between initial and final state, there's the pi that we had before, and the h bar. So you notice that I'm skipping over the slide very, very quickly, because I've never been happy with the arguments and the details, because we're basically doing exactly what the people have done before. We take the total amount of entropy that is produced, divided by the minimal time, and then we derive some bond. Conceptually, it's nice, because now we're really using arguments from quantum thermodynamics and the quantum speed limit, which is a more careful formulation of the Heisenberg uncertainty relation for energy and time. But at the same time, this cannot be a sound bound from various different reasons. So first of all, computing these kind of things without motivation, just I'm dividing something maximal by something minimal. Of course, we get an upper bound, but how do we know whether this bound is even reasonable or even close in the ballpark of what we want to estimate? And these two quantities are actually inconsistent. So in order to have this irreversible entropy production, you need driven dynamics, you need to change the Hamiltonian. Whereas this version of the speed limit that was available in 2010 is, strictly speaking, only defined for undriven unitary dynamics. So we needed to do better. So before I jump at the new problem, let me quickly recapitulate and bring you all up to speed to where we were at about a year ago. So what we have is we have these appealing bounds on the rate of entropy production that do tell us something about the conceptual framework, how all the things are tied together. What we've also seen is that there are various different approaches that allow us to connect these different quantities. Which means whatever we're doing here, bounding this rate of entropy production or information production or communication or whatever you want to call it, seems to be a somewhat universal problem of somewhat broad interest. And similar bounds, functionally, mathematically similar bounds, do pop up in various different areas. And it would be nice to somehow unify all of that and find a more underlying universal symmetry. But the issues that we have at this point is that all of the derivations that I've given you rely on plausibility arguments, and somewhat it's all hand-waving in the sense that either you bound the maximal of information in the universe or in a black hole, so to speak, small universe, or you simply assign an energy uncertainty to the information carriers, or you simply divide to somewhat unrelated quantities, namely the total entropy production under unitary dynamics, driven unitary dynamics, and divided by the quantum speed limit that comes from somewhere else. Which means none of these bounds that I've spoken about so far have a very clear applicability. In particular, we have no idea how to use any of these bounds in an actual problem in quantum technologies, how we're even going to compute any of that. Now, what we need to do, and this was actually my main motivation when I started getting into quantum speed limits, is we need to derive these speed limits. We need to look into driven system, open systems, and we need to better understand how dynamics are characterized. And once we have that, which did take the better part of a decade, we need to use whatever we obtain to more rigorously look into how to bound rates in entropy and information production. All right. Now, what I will have in mind for the following is really this control paradigm. So we have some red box, this is my quantum computer, the quantum system of interest, and we have some external control, some magnetic field that we can change, or some external control parameter alpha or lambda that we usually have in a thermodynamic setup. What we then want to look into is we have some initial state, psi or rho. If it's pure, I typically denote by psi. If it's mixed, I typically denote by rho. And then I want to drive the system from some initial time psi 0, psi naught, to some final state psi tau. And the question that I want to ask is, what is the maximal rate with which the quantum state changes under the given external control? This is what's often called the geometric approach or the control paradigm to quantum speed limits. So what you should have in mind is I drive my system from the outside, my quantum system does something in response to the outside driving, but I don't want to necessarily restrict myself to only unitary dynamics or Markovian dynamics. So I just have some black box that does something, some dynamics. For these systems, let me be a little bit more specific. The starting point of the analysis is this Mandelstam-Tamm or Morges-Levington time bound, which are, well, also 60 years old, 70 years old by now, at least the Mandelstam-Tamm bound. And this has been derived here in these two papers for time-independent dynamics, which means you have a time-independent control, just apply a constant field. But obviously, this can be generalized to many different situations. And just to give you a little bit of a flavor of what people have been looking into, so whenever you want to derive these quantum speed limits, you have a huge variety of different things that you can do. For instance, you can look into, for example, optimal control theory, which means you start asking the question, what is the optimal control such that you achieve the minimal time to go from initial to final state? You can then somehow rate the change of some angle, but the problem is, how do you even define the angle? So for pure states, it's reasonably clear, it's just the angle in Hilbert space. But once you go to mixed states and open system dynamics, you have a huge zoo of different notions of angle or distance or distinguishability that you can look into. And depending on what paper you look into, people seem to have favorites in the sense that depending on the question that you ask, you might find different notions of distinguishability or measures of distance on density operator space that do deliver different things. So either you want a Riemannian metric, or you want a monotone, or you want something that is tight. But well, you somehow have to make a choice. You somehow have to choose how to measure distinguishability. Once you do that, you somehow have to decide how you want to derive these quantum speed limits. And if you look into the literature, what typically people do is this. So you go, for instance, to Wikipedia, you look into mathematical inequalities. There's a set of, I don't know, 50 or so. And then depending on what you want to do, you use either the Cauchy-Schwarz inequality, the trace inequality, the triangle inequality, any of these, and then you get some quantum speed limit, which leads to a zoo of, I stopped counting, probably something like 100 different versions of quantum speed limits. Here in this topical review, we put together some of them. But the question that we now have to ask is, so this is all interesting, and all these speed limits have a specific purpose for specific questions. But the question that we need to ask in this particular context is, which version of the speed limit does actually help us understand, better understand thermodynamic problems, which means which version of the quantum speed limit does provide an insight into how to, about communication, which of these speed limits is directly related to entropy or information production. For what I will be doing is, it will prove useful to work with the trace distance. But again, this is mostly a choice that is mathematically convenient, as you will see. And to give you a little bit of an idea of how to derive these speed limits, so what you do is you choose some measure of distance. Here, the trace distance, which is given here. You find an upper bound of the rate of change. So you compute the rate of change under some dynamics. You don't have to assume anything about the dynamics. Can be unitary, can be non-unitary, can be Markovian, non-Markovian, can be linear or even non-linear, doesn't really matter. Just compute the derivative. You bound it by the magnitude of this derivative. And then under slight abuse of notation, you see immediately that the derivative is just given by a beast like this. Then further applying some inequality, in the simplest case, the triangle inequality, you immediately arrive at very, very simple versions of speed limits where the rate of change of this angle is determined by something that depends only on the eigenvalues of rho, where here this is the trace norm of rho, which means this is rho dot. So this is just the sum of all the singular values of rho dot. And again, this is just a snapshot of a derivation, and deriving quantum speed limits, it basically always works the same way. You bound the rate of change of your measure of distinguishability, here the trace distance, and then you choose some inequality, here in this particular case, the triangle inequality, to end up with something that looks appealing. What you then can do is this, you can integrate on both sides over some external control driving parameter, which are just parameterized here as time tau, but in essence, you just parameterize external driving from some initial to some final value. And then you can introduce this quantum speed limit, which is just given by the measure of distinguishability, quite generically, whatever you picked, here in this particular case, the trace distance, in something that comes from the dynamics, which is typically given by some time average trace norm, which may or may not have physical significance in the sense that you can relate that directly to thermodynamics. To give you a little bit more of a flavor how to think about these speed limits, if you have unitary dynamics, then this time averaged trace norm of rho dot is just given by twice the energy. Which means for unitary dynamics, what you have here is actually nothing else but the Margulis-Levin bound, just the energy uncertainty principle for energy in time, where in this particular case, I measure angles in units of radian over pi half. So this is just a sophisticated way of writing down the energy time uncertainty principle derived directly from the trace distance. And this is why I like to work with this particular representation, because it's mathematically very simple in the sense that I only have two quantities here on the right, which I can interpret rather directly in the language that we're familiar with. Okay, now the question is, what do we do with that? Can I use that bound in any meaningful way to say something about the rate of information production? And the way I do that is, if you open a book on quantum information theory, you will find interesting inequalities. In particular, there's Bain's inequality that bounds the difference of the von Neumann entropy between two different quantum states. So here, if I have the change of two different quantum states, I can interpret that directly as the beginning and the end point of some dynamics. And Bain's inequality then tells me that the difference of the von Neumann entropy between the initial and final state, the magnitude of that thing, is given by twice the trace distance times the logarithm of the dimension of the Hilbert space plus some small numerical constant that I won't be worrying about in the following. And here now you see by I picked the quantum speed limit in terms of the trace distance, because for this particular scenario, it becomes mathematically extremely appealing to relate the change of von Neumann entropy directly with this quantum speed limit in terms of this trace distance. If I had worked with any other measure of distinguishability, I would just have to work with some continuity points or something like that, but I could do that. Then what I do is I identify the rate of communication exactly like we did that before, which is then the change of the von Neumann entropy under this dynamics divided by the quantum speed limit time, again, including the log2 for units. And what I immediately find is that then the rate of communication is upper bounded by the logarithm of the Hilbert space, the measure of the Hilbert space. Okay, makes kind of sense. Somewhat, this is the capacity, quantifies the capacity of information that can be stored in this time averaged trace norm. Now let's stare at this a little bit and see what we have achieved. So we do have something like a Bremermann-Bekenstein type bound for quantum information. Why do I call that type? Well, this lambda here is related to energy, but not quite. So it's the time average trace norm of the generator of the dynamics, which only is directly related to energy in unitary dynamics. The derivation is rigorous and unambiguous in the sense that I don't need to rely on black holes and traversing event horizons or something like that. Everything that I do is I just pick a specific dynamics, and then all the quantities come directly from a result from quantum information theory. Now, what did we set out to do? So I tried to motivate all of that with a quantum thermodynamic justification in the sense that we would like to bound rates of information production in terms of thermodynamic notions. Well, we're not quite there. In particular, for this bound here, the relation to thermodynamics is maybe somewhat questionable. However, what we can see is, as if we were, for example, in some kind of microcanonical ensemble, then the logarithm of the Hilbert space would be directly related to the microcanonical partition function, which means what we're looking here at least in closed system close to equilibrium, this is somewhat related to the Boltzmann entropy, maybe. But an immediate problem that we run here into is, so if you think about, for example, the systems that people have looked into, for example, in yesterday's days. So either you have something like qubits, and then this log of the dimension of the Hilbert space is simple, it's log2. That's something that we can work with. But if we have something like harmonic oscillators, where we have infinite dimensional Hilbert spaces, well, this bound is totally useless, because then the rate of communication is upper bounded by infinity. So what is that good for? This is why I decided that this needs additional study. But before we do that, I wanted to at least get an intuition for whether this bound can be tied at all. So as I just said, for harmonic oscillator, the bound is infinity, but for qubits, can we actually say more about that? And here you just see an illustration for this bound for the damped James-Cummings model, which I chose not to write on here because you're all familiar with it. It's actually the textbook example. You know that the dynamics is analytically solvable, and you have Markovian and non-Markovian regimes. So in the strong coupling regime, the dynamics is non-Markovian. What I plot here is the upper bound in red and the exact rate of change of the information in blue. And what you see here is that in the Markovian regime for weak coupling, the bound is actually pretty good. Honestly, when I first derived that, I did not expect that because I'm still working with Fain's inequality and the triangle inequality, and I had no intuition for how tight these bonds are, but it's not that bad. And what we also find is that in the non-Markovian regime, the bound is actually very bad because the actual rate of communication, rate of information production goes to 0, which we also can understand is because in the non-Markovian regime, you have this information backflow, which means the entropy starts oscillating, and then the time average of that thing just goes to 0. Whereas the upper bound does not pick up on these oscillations. But at least in the Markovian regime, this is not so bad. This is a good starting point. Now looking at this plot, so this is finite. All right, great. This is what we would have expected for a qubit. But now if we go to an harmonic oscillator, this red curve actually would be strictly at infinity because the dimension of the Hilbert space is infinity. So that doesn't really help. Luckily, not that many years ago, 5 years ago, Winter derived a generalization of Fain's inequality for infinite dimensional Hilbert spaces, where then the change of the phenomenon entropy between time initial and final state is again given by twice the trace distance. That's great. But now times the maximal entropy under a given energy of the system. And as you know, the state that maximizes the entropy is the Gibbs state. So what we have here is now that the change of the phenomenon entropy is given by twice the distance between initial and final state and the maximal entropy that can be carried at a given energy. Using the same arguments as before, you can derive, again, a similar bound on the rate of information production, which looks now even more appealing than what we had before. So we have the same quantities, Kb, log2, all of that. But now what I called Boltzmann entropy in the previous slide here, that thing, which is related to the Boltzmann entropy, is now replaced by the Gibbs entropy at a given energy of the system. So what do we have here? We have a Bremer-Beckner-type term for infinite dimensions, right? But it also somehow illustrates more the thermodynamic consequences and potential of the system in the sense that here we have something of a canonical bound versus a microcanonical bound that we had before. So I call that more thermodynamic bound on information production. But again, question mark, because I do think that this needs further analysis and better understanding of what we're looking at. But this is a very good starting point. Now, I'm sure that some of you already are uncomfortable with these things because, well, all of that actually only makes sense if we have open system dynamics, right? In unitary dynamics, the change of phenomenon entropy would be 0. I started motivating all of that with quantum technologies, where we work very, very hard to keep things as unitary as possible. So the remaining question that we need to ask is, can we actually say something about isolated systems? So the problem is, most computations are formulated for unitary dynamics. The phenomenon entropy is constant, doesn't help. However, what we can do is for unitary dynamics, we can look into the Shannon information for marginals, which means we're looking into the entropy that is carried by the post-measurement states. Measure, get post-measurement state, and then you compute the entropy of that. There might be some thermodynamic relevance. So some of you might be familiar with the diagonal entropy and energy representation, and that's just the Shannon information for the marginals after energy measurements. Luckily, also 5 years ago, another Fain's type inequality was derived for the change of the Shannon information under some observable x, where again, sigma and rho are my initial and final states. These things look, again, very appealing. We have some prefactor that I won't be worrying about too much. It just comes from the geometry of the quantum states times the Wasserstein one norm, which I will specify on the next slide. So what we get is this also for these marginals, we essentially have the same Feinstein inequality, where the only thing that we need to worry about is we need to replace the trace distance with the equivalent of the trace distance for probability distributions. So this is what the Wasserstein P distance looks like. So you immediately see that if P equals 1, and this is just a generalization of the trace distance for probability distributions or for marginals, you can derive quantum speed limits similarly to what I did before. So you look into the rate of change of that thing, you upper bound it by the magnitude, you get exactly the same expression that I had before, where just the trace is now replaced by the sum or integral depending on whether the spectrum is discrete or continuous. Using the same inequality, the triangle inequality, then you can upper bound this rate of change of the Wasserstein 1 norm by a Wasserstein 1 distance by the Wasserstein 1 norm of the rate of change now of the marginal. So we get a quantum speed limit. This is a quantum speed limit that probably not even the experts in the audience of speed limits have thought about a lot. But we can derive speed limit times not only in density operator space, but also for marginals, where we need to replace measure of distinguishability now with things that actually live on the space of probability distributions. In complete analogy to what we have in density operator space, we now have time averaged quantities which are related to the norms that induce the measure of distinguishability that we look into. Using the same arguments as before, we then can upper bound the rate of information production along these marginals with exactly what we had before, where everything is just determined in terms of the rate of change of this Wasserstein 1 distance. What we had previously was that this alpha was directly related to either some Boltzmann or Gibbs type entropy of the quantum system of interest. Here, the situation is less clear simply because this Fein's inequality is written in terms of this alpha, but well, it requires more work, but at least for Gaussian states, this can also be related directly to some entropic notion. Now, what do we have? So, sorry, this is actually a typo here. So what we have is we have these Perelman-Bekenstein type bounds not only for mixed state evolution, open system dynamics, but also for unitary dynamics. We have some kind of thermodynamic identification of information production, but as I said, this is maybe only a starting point because these quantities, these time average trace norms may or may not be of thermodynamic relevance. And there's a lot of work in the literature on how to interpret these, but I don't think I'm comfortable yet try to present a consensus here. But some of you may be familiar with the idea that this is directly related to the heat current into the environment or entropy currents. But that really needs further study and analysis. What I did in this paper was mostly derive these mathematical points, which I do think provide a very, very good starting point for a thermodynamic analysis. Now, rounding this talk off, I wanted to come back to, well, season of grad school applications. And since Camille suggested that I could either give a technical talk or a colloquium talk, I chose to do both in one. I'm not sure if that was a wise idea, but you tell me. So I want to use the remaining 2 minutes just to give you a little bit of an idea of the other things that we're working at UMBC. So yesterday you already heard Nathan talk about quantum engines. The other things that we're interested in, so this is what I spoke about today, Heisenberg and central relations for energy and time, where we're not only interested in bounding entropy production rates, but we're also interested in very thermodynamic problems like, for example, thermometry and metrology. In particular, there's some ongoing collaboration with an experimentalist who just moved to Dresden, who's planning to use some of these ideas to better understand to what precision you can measure temperature in nanostructures. The other things that we're doing is we're working on foundations of statistical mechanics, which means we're trying to better understand really the resources and the underlying physical foundations of thermodynamics and statistical mechanics, which arise out of entanglement. And this necessarily also leads us to think about how to apply many of the things that I spoke today about in quantum chaos, in the sense that quantum chaos describes the spread of information, and spread of information obviously is directly related to information production over subspaces, for which we do need to understand thermodynamics. And some of these things can be directly demonstrated, for example, on IBM's quantum experience or on D-Wave. Then finally, we're also interested in thermodynamically optimal processes. I'm not sure if we're going to have talks on shortcuts in this workshop, but this is certainly something that you've heard about. But what I'm more excited about are linear response techniques that directly, again, tie into, and this is why I'm talking about this today. So entropy production or information production can always be expressed directly in terms of Onsager coefficients, linear response theory, right? This is what you do in a standard textbook. You pick up something like Callan, look into entropy production rates. What you find is that this is expressed as a bilinear form in terms of the Onsager coefficients. Now what we have here, and this is something that we need to better understand, is how to relate these entropy production rates in terms of these response functions, these kinetic coefficients, and how these kinetic coefficients carry information about the underlying quantum dynamics. This is a very exciting area of research. And then finally, things that we're doing is, so we're applying many of these ideas in somewhat outside the box systems. In particular, we're working on what we now call quantum-inspired evolutionary biology, where we're using all of these ideas, again, information production, control, and thermodynamics, to say something about systems that might not necessarily come to mind. In particular, we're using the mathematical framework, the mathematical toolset developed for quantum systems to optimize reaction networks in biology. This brings me to the end of my talk. So if you forget everything that I said today, what I would like you to remember is I did talk about Bremer and Bekenstein and how these relate to information and entropy production rates. What I suggested was that these entropy production rates can be described entirely in terms of quantum information theory and quantum speed limits. And what I do hope to convince you of is that we now have a very good starting point, very promising starting point for a more thermodynamic analysis of entropy production rates, in that there are genuine quantum effects to consider when thinking about fundamental limits of how fast systems can dissipate. This is the team. This is a picture that I took exactly a year ago before the whole world went to hell, which is, when we were still all in Maryland. I think to date, we're distributed across 4 continents, if I'm not mistaken. And yeah, so that's them. And if you think this is exciting research, that you have something to publish, and you're looking for a good venue for that, we have currently 2 special issues open, one in entropy, which is more on the quantum side of things, and one in statistical physics, which is more on the information side of things, with deadlines for the special issue in entropy end of January. But here we can be reasonably loose because of the current situation. And here the deadline is in April. Thank you.
Okay, thank you, Sebastian, for your nice presentation as usual. And then it's time now to take up questions from the audience. During the talk, Steve raised up hand. So I don't know, Steve, if you still want to go on with the question. So we don't have any question in the chat or question and chat. So
yeah, I have a question indeed.
okay.
Yeah, no, I was so yeah. Unless I missed something, in the most part of your talk, you are in fact talking about the difference between entropy, right?
Right.
Between the state, and so it's different from what sometimes it's called the entropy production. Meaning, yeah, I mean, yeah, as we all know, you can divide the change of entropy in a system as part. It's an exchange of entropy between the system and the external world, and really a part which is creation of entropy, probably related to the increase of correlation or something like that. And yeah, so I was just wondering how, I mean, if you are thinking in relating this, I mean, yeah, because there's a lot of work also done to really specifically about entropy production, in that sense, like the entropy production, which is, yeah, really related to irreversibility. And so, yeah, how you think you can relate both, or yeah.
So everything that I did here was for changes of von Neumann entropy or for changes of the standard information over marginals. This is why in all of the titles of the slides, I always call it information production, in the sense that it's changing the information, it's producing information. What you're referring to is the natural splitting of fundamentally different contributions to the entropy, which means whenever we change the von Neumann entropy, there's going to be a change of entropy that's just due to internal mechanisms, what you would call the irreversible entropy production, and the external entropy, which at least for quasi-static processes is related to the exchange of heat with the environment. What I do think would be an important problem is understanding the different contributions of entropy and how their rates are characterized in terms of the quantum speed limit. We haven't quite done that yet. We have some initial results. So there's a paper on the archive right now with my Brazilian collaborators, Marcos Bonanza and Pierre Nazé, in which we do look into the entropy production rates within this linear response framework that I mentioned here. Where's it? This one here. What we haven't done yet, which is on our to-do list, is better understanding this irreversible entropy production and the rates of irreversible entropy production in terms of quantum dynamics, which is an open question. Some of these things have been outlined actually here in this paper, in this quantum science and technology, but in the context of quantum chaos. So why am I telling you all of this? So the best that I can tell you right now is we're thinking about it. We have a couple of preliminary initial results where we're trying to come to the problem from many different directions. But, and now this is why I'm actually talking about these papers. All of them came out in 2020, which means we're thinking about it, but we're not going to tell you anything before 2021. So stay tuned.
Okay, thank you.
Okay. In absence of another question, let me just follow up. If I understand one, this quantum speed limits time. So you usually have this one, related to fluctuation, and then the other one to the mean energy.
Mm-hmm.
So then in this situation, if I understand, then it seems so the maximum is the one related to the mean energy. So which is why it appears in the expression, or is it the one related to the variance, the fluctuation?
So in this particular case, everything is given in terms of the trace distance here.
Yes.
The trace distance gives you the sum of all the singular values.
Okay.
Which means if you have time in them, so if you have undriven Hamiltonians that are positive semi-definite, then that thing is directly related, or is actually exactly given by the mean energy. However, the reason why I'm looking at this bound is because of the choice of distance, the choice of measure of distinguishability, the trace distance. If I had worked with a quadratic measure of distinguishability, like for example, the Euclidean distance, Hellinger distance, or something like that, I would have ended up with the square in here, which then would have been directly related to the variance of the energy. So, and this is what I was trying to illustrate. It really depends on how you derive these bounds. You have this huge choice, so you have all this plethora of different approaches. And depending on what you choose, you're going to get a different bound. It doesn't mean that these bounds actually are physically any more meaningful than the others. What one really needs to think about and worry about more is which of these bounds carry the information that gives you an answer to the question that you're asking. And if you set out to ask a specific question about the mean, well, then you want to work with something like the trace distance. if you set out to ask a question about the variance, then you need to work with a measure of distinguishability of a distance that is quadratic in the quantum states.
So we have a question from Felix Bender. So should we have that question live or Camille? Maybe if you can put him on.
Yeah, or maybe you can just read it.
Okay, so Sebastian says, is there an operational interpretation or reformulation of your results? Can they be rephrased for a communication scenario?
I hope so, but I haven't done it. So, right, I mean, so I've been talking a lot about communication because information production or changes of information, this is typically what you would be interested in communication. But I actually haven't formulated directly in terms of communication channels. So something that my student Akram has been looking into a little bit, but in a very, very different context. But so my answer is, my best possible guess is yes, it should be possible, but we haven't done it yet.
Okay, so in absence of further questions, so we thank Sebastian for the presentation, and we move to the next speaker.